You look up, see that faint smudge in the sky called Andromeda, and your brain quietly whispers, "We'll go there someday." No, you won't. This is the story of a destination so far out of your league that even your wildest sci-fi instincts are playing in the kiddie pool. Stay with this, because once you see what Andromeda really is to a species like ours, every casual "will just go to another galaxy" line is never going to sound the same again. You hear that Andromeda is 2.5 million light years away, and your brain quietly files that under "very far" and moves on. That reaction is the problem. A light year is already an extreme unit. One light year is about 9.46 trillion kilometers, roughly 5.88 trillion miles. That is the distance light covers in 1 year, moving at about 300,000 kilometers per second, around 186,000 miles per second. Andromeda is not one of those. It is about 2.5 million of those in a row. That works out to roughly 24 quintillion kilometers, or about 15 quintillion miles. Written out, that is a 24 with 18 zeros after it. When you look at it that way, every huge distance you have ever heard, from Earth to Moon, Earth to Mars, even the distance to Pluto, barely registers next to Andromeda. They are details inside your own backyard, while Andromeda is on another continent, across an ocean you do not even see. So the first hard point is this. You are not talking about a long trip, you are talking about a scale of distance your brain never evolved to deal with. Earth to Moon is about 384,000 kilometers, around 239,000 miles. Mars, depending on the orbits, can be 50 to 400 million kilometers away, tens to hundreds of millions of miles. Voyager 1, our most distant probe, is a little over 20 billion kilometers out, about 13 billion miles. Those numbers already feel big, they already feel like space. But if you put 20 billion kilometers next to 240 trillion kilometers, it is like comparing a single step to the distance around the planet. You could line up thousands and thousands of Voyager 1 distances, and you still would not reach even a tiny fraction of the way to Andromeda. Then you might ask, alright, but we can go fast. How fast can our best machines actually move? Right now, the record belongs to NASA's Parker Solar Probe. When it swings close to the Sun, it reaches speeds of about 190 kilometers per second, roughly 430,000 miles per hour. That is far beyond any plane, any normal spacecraft. It covers the distance from New York to Los Angeles in under a minute. By engineering standards, that is extreme. By intergalactic standards, it is painfully slow. At 190 kilometers per second, crossing a single light year still takes more than 1,500 years. 1 light year, not millions. That is longer than all of the recorded human history. Now, attach that to Andromeda. Take 1,500 years and multiply it by 2.5 million light years. You end up with travel times in the ballpark of 3.8 billion years at Parker Solar Probe speed. For context, complex animals on Earth, things like worms and early fish, only started to appear around 600 million years ago. You're talking about a journey longer than the entire history of complex life on this planet. So when someone says, "We just need a faster rocket," you can see how weak that sounds when even our fastest hardware barely makes a dent in the problem. And this is still being generous because we quietly skip the fact that humans are not riding that probe. You cannot just strap people onto a Parker-style orbit and call it a day, but leave that aside and focus on the next hard limit, the speed of light itself. Light needs about 2.5 million years to get here from Andromeda. That is why astronomers say we are seeing Andromeda as it was 2.5 million years ago. When those photons started their trip, early humans on Earth were not building cities or writing stories, they were just beginning to use very simple stone tools. Now comes the key point. Even if, against the rules of physics, you could move at light speed, your trip to Andromeda would still take those same 2.5 million years in the external universe. You're always late. The galaxy you see in the sky is already ancient by the time its light reaches you. and the version you arrive at millions of years later has shifted again. Star positions have changed, some stars have died, new ones have formed. You're chasing a target that never stands still, and even at the universe's speed limit, you're stuck with million-year travel times. Your everyday experience pushes you to think in a simple, linear way. Double the distance means double the time. Triple the distance means triple the time. That works for driving between cities, maybe for long flights. It breaks completely when you scale up to intergalactic ranges. The travel time to Andromeda is not a larger version of a road trip, it sits in a different category. You stop measuring in hours, days, or even centuries, and you start measuring in things like geological eras and evolutionary cycles. Over a few billion years, continents drift, mountain ranges rise and erode, entire types of life appear and disappear. Talking about that much time for a journey makes the word journey feel wrong, because nothing about your starting point is recognizable anymore by the time you arrive. So you might try to compromise. You might say, fine, not light speed, but something like 10% of it. That sounds high, but maybe not impossible for a future civilization. 10% of light speed is about 30,000 kilometers per second, roughly 67 million miles per hour. That is way beyond anything we can build right now. It would need a completely different kind of propulsion, but let's grant it as a thought experiment. At that speed, crossing a single light year would take roughly 10 years, ignoring acceleration and braking. 10 years per light year suddenly sounds more human, more like a mission a lifetime could at least relate to. Then you plug in the real number again, 2.5 million light years. 10 years per light year times 2.5 million gives you about 25 million years of travel time one way. 25 million years ago, there were no humans at all. The creatures walking Earth were early primates and strange mammals that you would not recognize. So even at 10% of light speed, the people who arrive in Andromeda are not the crew in any normal sense. They are distant descendants, changed genetically, culturally, technologically, maybe to the point where they would not even see themselves as the same species as the ones who left. And remember, 10% of light speed is not a minor upgrade from Parker Solar Probe. It is more than 100 times faster. Getting a ship with humans on board to that speed is not just a question of better engines, it is a problem that involves absurd amounts of energy, extreme engineering, and huge safety issues. That is before you even start talking about slowing down at the other end, or surviving the journey in between. So here is where this first part leaves you. Ignore fuel for a moment, ignore radiation, ignore wear and tear, look only at distance and speed. You are trying to cross about 24 quintillion kilometers or 15 quintillion miles. With our fastest existing hardware, that takes billions of years. With extremely optimistic future tech speeds, it still takes millions of years. That is why calling Andromeda far was misleading. It is not just far, it sits in a regime of distance where all our normal ideas of travel time collapse. And this leads straight into the next problem, which is even harsher, because you're probably thinking, maybe we just need to push harder, build a stronger engine, burn more fuel, get closer to those extreme speeds. The moment you ask, what kind of rocket would I actually need to do that? You run headfirst into the rocket equation, and that is where the dream of just going faster turns into a nightmare of impossible fuel requirements. You think the fix is simple, just build a bigger rocket, burn more fuel and push harder. This is where the universe leans in and says no. The problem is not motivation, it is exhaust velocity, the speed at which you throw stuff out the back of your rocket. That speed is the lever that controls everything, and for the rockets you actually know how to build, that lever is short and stubborn. Chemical rockets, the ones you use now, throw exhaust out at only a few kilometers per second, maybe 3 to 4.5. Nuclear thermal rockets, where you heat hydrogen with a reactor, might give you something like 8 to 10 kilometers per second of exhaust speed. That sounds like an upgrade, but the numbers you want for Andromeda are a lot closer to thousands or tens of thousands of kilometers per second, not 10. Here's the key rule, the rocket equation in plain terms. The speed your rocket can reach depends on how fast you can throw mass out the back, and on how much propellant mass you start with, compared to how much dry rocket and payload you have left at the end. The relationship is not linear. Each extra chunk of speed costs more propellant than the last chunk, and you also have to carry the propellant that will be burned later, which makes the ship heavier and demands even more propellant. You get this loop where trying to go really fast makes your fuel requirement explode. So if your exhaust is moving only 10 kilometers per second and you say, I want my ship to end up going thousands of kilometers per second, you are asking your rocket to push you to a speed hundreds of times higher than the speed of the exhaust it throws away. With the rocket equation, that means your starting mass has to be insanely larger than your final mass. Not 10 times, not 100 times, but numbers so large that almost everything you launch is just fuel, and the actual ship and crew are a tiny speck tucked inside. Push that goal up toward even 1% of light speed, about 3,000 kilometers per second, and with chemical or simple nuclear thermal exhaust speeds, the required mass ratio goes from ridiculous to basically turn most of the solar system into propellant. Think about Saturn V, the moon rocket. It had a mass on the pad of about 3,000 tons to send around 140 tons into low Earth orbit, a mass ratio of roughly 20 to 1. With staged burning, that was enough to send a small spacecraft to the moon, about 384,000 kilometers away. Now stretch the scale. You keep the same basic idea, stacked stages, similar exhaust speeds, the same kind of chemistry. You want to cross not hundreds of thousands of kilometers, but about 24 quintillion kilometers. The numbers do not just get millions of times worse, they get exponentially worse because every extra bit of speed multiplies the propellant need. If you tried to design a Saturn V-style system for intergalactic travel, the mass of fuel you need quickly climbs past anything you could physically build. The moon rocket, which feels massive to you, becomes irrelevant on Andromeda scales. So you turn to the next step, you go nuclear in a much more aggressive way. Concepts like Project Orion replace chemical burning with nuclear explosions, setting off small nuclear bombs behind a metal plate and riding the repeated kicks. In theory, with strong enough engineering, you might push a vehicle to a few percent of light speed, maybe around 3%, something like 9,000 kilometers per second. That completely outclasses chemical rockets. But now you plug that speed into the distance you already know. Andromeda is about 2.5 million light years away. At 3% of light speed, you cover 1 light year in about 33 years. Multiply that by the 2.5 million, and you get on the order of 80 million years of travel, one way. So even if you solve all the engineering around firing off nuclear bombs in space, and you build a ship that can survive that, the travel time is still tens of millions of years. You've upgraded your trip from completely impossible to still completely impossible for human lifespans. Maybe you push in a different direction and say, forget brute force bombs, go for ultra-efficient engines like ion thrusters. Ion engines throw particles out the back at very high exhaust speeds, tens of kilometers per second, sometimes more than 50. The catch is thrust. Ion engines push very gently. They are perfect for slowly adjusting a probe's orbit, or for a long, patient spiral out from Earth over years. But for a human-scale ship with thousands of tons of mass, the push is so small that you would spend decades just crawling up to a modest fraction of light speed if you could ever get there at all before something breaks or runs out. These engines are tools for fine maneuvering inside a solar system, not for sprinting between galaxies. Under all of this sits the same harsh pattern. Pushing closer to light speed is not like turning up a volume knob. Each extra percent of light speed you aim for costs much more energy than the previous percent, and for rockets that carry their own fuel, that means much more propellant. The math behind the rocket equation is not a guideline you can negotiate with. It says that if you rely on pushing exhaust out the back and that exhaust has a limited speed, then trying to reach even 1% of light speed already strains you to the point of needing absurd mass ratios and massive energy budgets. Going beyond that toward 10% or more is not just harder, it is a different level of impossible. So when you hear people say, we will just build a more powerful engine and go to the stars or even to other galaxies, this is the wall they are hitting. With the propulsion methods you understand today, Chemical, nuclear thermal, nuclear pulse, ion. You can play inside the solar system, maybe reach nearby stars with very exotic designs. But pushing a human ship toward Andromeda with any of them takes the mass and energy problem from very tough straight into beyond any realistic rocket-based civilization. And that leads straight into the next question. Even if you pretend the rocket equation problem away for a moment, and you somehow get up to a decent fraction of light speed, how much raw energy do you need to give a starship that kind of velocity? And can a human civilization ever pay that bill without tearing itself apart? How big is the power bill to push a real starship to serious speed, not just around the solar system, but toward another galaxy? Take a ship that is huge by today's standards, but not crazy for a future civilization. About 1,000 tons, which is 1 million kilograms, roughly the mass of a large ocean ship. Now give it a cruise speed of 10% of light speed, about 30,000 kilometers per second, roughly 67 million miles per hour. The kinetic energy locked in that moving mass ends up around a few hundred billion joules, on the order of 10 to the power of 20. That is comparable to the total energy humanity uses in an entire year. All power plants, all cars, all factories, but everything combined. And that is just to speed the ship up. If you ever plan to slow it down near Andromeda, instead of letting it shoot straight through intergalactic space forever, you need roughly the same energy again in reverse. Then you add in efficiencies because no engine is perfect, and safety margins, and reserve power for life support and emergencies, and the real energy budget climbs far beyond that simple number. So why not just crank up the speed further and deal with a bigger bill? The trap here is how kinetic energy scales with speed. At low fractions of light speed, the energy you need grows roughly with the square of the velocity. Double the speed, and the energy requirement does not double, it multiplies by 4. If you go from 10% of light speed to 20%, you have not just asked for twice as much power, you have asked for 4 times as much. Push to 50% of light speed, and the multiplier compared to 10% is around 25. On top of that, as you climb closer to light speed, relativity kicks in, and the energy grows even faster than that simple square rule. The universe charges you a sharper and sharper price for every upgrade in speed. The first few percent of light speed might be barely in reach for some advanced future tech. The jump from there to, say, 30 or 50% is a completely different class of problem. Maybe you answer that by reaching for better fuel. Chemical fuel, like the stuff in rockets today, gives you a few dozen million joules per kilogram of propellant, which is not much on this scale. Fusion, the process that powers the sun, offers around 10 million times more energy per kilogram of fuel. You fuse light elements like hydrogen into heavier ones and gain a huge energy release. On paper, that sounds like the perfect solution. Compact fuel, massive energy output, exactly what a starship needs. But then you match that against Andromeda's distance and the speed you want. To get a big, shielded, life-supporting ship up to a decent fraction of light speed, and then slow it down again near the target, you are not burning a few tons of fusion fuel. Even with very optimistic engine efficiency, you're talking about chewing through masses comparable to asteroids or moons, if you want multiple missions or bigger ships. If you aim to cut a few zeros off the travel time, going from tens of millions of years down to maybe a million, the fuel mass and energy demand ramp up until you are effectively converting entire planetary bodies into starship propellant. At that point, you're no longer talking about a big power plant, you're talking about civilization-level control of energy. On the Kardashev scale, a Type 1 civilization can use all the energy available on its home planet, roughly 10 to the power of 16 watts for Earth. Type 2 can use the full output of its star, around 10 to the power of 26 watts for the Sun. Type 3 can tap the energy of an entire galaxy. For a single serious Andromeda mission with a crewed ship moving at a high fraction of light speed, you start drifting toward Type 2 style demands just to fuel, launch, and support that one effort at a reasonable cadence. You either run your entire planet's energy economy for many years or centuries just to charge up this one project, or you surround your star with vast collectors, something like a Dyson swarm, to harvest a large fraction of its output. Humanity is not even firmly at Type 1 yet. We are still at the stage where our total power use is a small fraction of what falls on Earth from the Sun, and even that is not the end of the problem, because you do not just need to reach these insane energy levels once in a huge, explosive stunt. You have to do it in a controlled way, with safety margins repeatedly, and without destroying the environment or the civilization that is paying the bill. Lighting a match is easy. Running a continent-sized nuclear plant safely for thousands of years is hard. Now scale that up again. You need generators, reactors, or stellar-scale collectors that can channel these huge energies into your drive systems without constant catastrophic failures. You need energy storage or transfer systems that do not lose most of the power as waste heat. You need to be able to spin this up and down on demand, launch after launch, while your homeworld still runs industry, food production, climate control, and everything else. A one-time reckless burst that melts half your planet in the process is not a viable Starflight program. So even before you bring in the biology, the psychology, or the material science problems, the energy numbers alone already push an Andromeda mission into a level of effort that looks less like a big engineering project and more like reorganizing your entire civilization around a single task for ages. And that raises the next uncomfortable question. Even if you somehow learnt to handle power on that scale, could the humans you send or their descendants actually live long enough, stay stable enough, and stay focused enough to survive a journey that still takes millions of years? Here's the next hard problem. Your body runs on decades. The trip to Andromeda runs on millions of years. Average human life expectancy right now is under 100 years. Be generous, say future medicine pushes that to 150 or even 200 years. A 10 million year journey to another galaxy takes that number and turns it into background noise. Your entire lifespan is a rounding error on the mission clock. You are not sending a crew in any normal sense. You are sending a moving population that lives and dies while the ship crawls through space. Think about the scale for a second. 10 million years is 50,200-year lifetimes stacked end to end. In that time on Earth, species appear, dominate, and vanish. Ice ages come and go, coastlines change. A single human, even a long-lived one, cannot go to Andromeda. You would be born on the ship, live your whole life on the ship, and die on the ship with the galaxy you're heading in for, never changing more than a faint blur in the telescope. The mission isn't one story, it is thousands of overlapping stories, generations deep, all trapped in one moving habitat. So if one human lifetime is basically irrelevant, what do people usually propose to fix that? And why does that answer open a new set of problems instead of solving anything? The standard idea is the multi-generation ship, not a fast sprint, but a slow arc. Hundreds or thousands of people live on board, have children, those children have children, and so on, while the ship just keeps going. Nobody who steps on the ship at launch expects to ever see Andromeda. For them, the ship is home permanently. That sounds clean and logical in one sentence, but when you zoom in, it is brutal. We have never run a sealed, closed ecosystem experiment for even 100 years without outside help. Projects like biosphere-style habitats struggled over just a couple of years, with oxygen levels drifting, carbon dioxide building up, and unexpected ecosystem crashes. Now scale that to 10,000 years, or a million years. You need air, water, food and waste cycles that stay balanced, while hundreds of generations come and go. You have to prevent social collapse in a metal environment where nobody can leave, ever. You have to handle crime, mental health, education and conflict for people who are born into a mission they never consented to. It is not a space cruise, it is a city you can never step outside of, moving at tens of thousands of kilometers per second through a hostile vacuum. We have zero real data on how a closed human society behaves over even 1,000 years, let alone over the timescales you need for an Andromeda trip. And that is before biology itself starts to push back, so how long can your DNA and your bodies stay stable when you stretch them over millennia? Biology does not stand still. Every time cells divide, DNA copies itself, and copying is not perfect. You get small errors, mutations. On Earth, those are managed by repair systems and by natural selection across large populations. In a ship with maybe a few thousand people under constant low-level radiation exposure from space, those errors add up. You get higher risks of cancer, infertility, genetic diseases. To keep genetic health stable, you need a large breeding population, strict control over mating patterns, or constant genetic engineering corrections. All of that has to run for millions of years without serious mistakes. Radiation is another constant hit. Even with good shielding, cosmic rays punch through, causing DNA damage. Over hundreds of years, you can maybe manage that with medicine and careful shielding design. Over millions of years, you're playing a never-ending defense game against mutation and drift. The small population also means genetic drift, where random changes in gene frequencies slowly push your group away from the original human baseline. After long enough, the people on that ship may be physically and mentally different, in ways you did not plan. Evolution is happening inside a metal can, and it does not care about your original mission profile. So then you might try to jump outside of normal biology completely. If living for millions of years is impossible, can you just skip the years, put people on pause, and wake them up at the other end? Cryo-sleep or suspended animation sounds like a neat shortcut, but right now it barely exists as a concept for humans. We can cool small animals or organs for short times, but a full human, frozen for decades or centuries, is already far beyond what medicine can actually do. Cells are full of water and complex structures. If you freeze them carelessly, ice crystals form and rip them apart. Even with advanced techniques, you still face long-term chemical breakdown, slow reactions that continue at low temperatures, and mechanical stress from cooling and heating cycles. Now stretch that to 1 million years, or tens of millions. Even if your cryo method avoids ice crystals, atoms are still moving, bonds are still slowly changing, radiation is still striking the body. The ship itself is not perfectly stable. Materials shift, containers degrade, power systems fail. 1 million-year sleep is not a restful pause. It is an extremely long, slow decay process, where you hope your control systems never slip. One failure in temperature control, one crack in a tank, one long-term drift in chemistry, and your frozen crew is just very cold biological waste. Cryo-sleep does not escape the timescale problem. It just hides it inside frozen hardware that still has to survive for geological ages. Then some people push the idea even further. If bodies are the weak point, why not drop biology entirely and turn humans into software? Does that finally beat the clock? Uploading minds into machines, if it ever becomes possible, just trades one set of limits for another. Now your people are patterns in hardware, running on processors stored in memory. But those processors are made of physical materials. They sit on circuits that age, heat up, and suffer damage from radiation. Cosmic rays that used to hit DNA now flip bits in memory, corrupt data, and cause random errors in the code that defines your consciousness. Over millions of years, even a very robust system needs constant error correction, redundancy, backup copies, and repair. You still have to power the hardware, maybe with reactors or captured starlight, and those power systems still wear out. You still need factories on the ship that can rebuild chips, boards, and mechanical parts from raw materials. Those factories themselves have control systems and software that can drift or fail. In other words, you have not escaped fragility, you have moved it from flesh to metal and silicon. The underlying problem is still there. You're asking any complex system, biological or mechanical, to remain functional and organized for time spans that normally erase mountains and wipe out species. So when you line everything up, short human lifespans, unstable multi-generation societies, DNA damage, the limits of cryo-sleep, and the fragility of machines, you get the same answer from different angles. Human-scale life is built for tens of years under 1G on a safe planet, not for millions of years in deep space. Before rockets, before exotic engines, the basic mismatch between how long you live and how long Andromeda takes to reach is already enough to make the trip practically impossible. You hear between galaxies and it sounds like pure emptiness, just black nothing stretching forever, so how bad can that be to fly through? The catch is, almost empty turns into constantly dangerous the moment you push up towards serious speed. The average intergalactic space has only a few atoms in each cubic meter, maybe a few stray dust grains here and there. That sounds harmless at walking pace. At 10% of light speed, about 30,000 kilometers per second, roughly 67 million miles per hour, every one of those particles hits your ship with ridiculous energy. A grain of sand at that speed slams into your hull with the punch of a small artillery shell. You are not gliding through a calm vacuum, you are driving into an invisible storm of microscopic bullets, non-stop, for millions of years. You only need a tiny fraction of those impacts to get through your shield before parts of your ship start to fail in ugly ways. So the obvious question is, if the dust and gas are already that bad, what about the higher energy stuff flying around out there? The particles that are not just moving fast but almost at light speed themselves. Cosmic rays are your next problem, and they do not care about your schedule. These are high-energy particles, mostly protons and heavier atomic nuclei, shot out by things like supernovae and black hole jets. They move at speeds close to light, and they hit with enough energy to punch through solid matter and tear up atoms along their path. On Earth, you barely notice them because our planet has a thick atmosphere and a magnetic field that deflects or slows most of that radiation. In deep intergalactic space, there is no atmosphere, and your ship's magnetic field, if it has one, is tiny compared to Earth's. Over a mission of a few years or decades, even getting acceptable radiation doses for astronauts is hard. Over millions of years, or tens of millions, there is no known shielding setup that looks remotely good enough. You can try to wrap the crew section in thick layers of material, but then you hit the next brute force limit. How heavy can you make the shield before it kills your mission another way? Shielding works by giving radiation and particles something to hit before they hit you. Water, ice, rock, or metal, like aluminum or steel, can all help. Put a few meters of water or rock around the living spaces, and you cut down the radiation exposure a lot. But every extra centimeter of protection is extra mass. A cubic meter of water weighs about 1,000 kilograms, around 2,200 pounds. Cover a large habitat with a multi-meter shell of shielding, and very quickly your protective layer alone weighs millions or billions of kilograms, which is millions to billions of tons. At that point, your ship starts to look more like a small asteroid, with a city hollowed out inside. Now remember the rocket and energy problems from earlier. Every kilogram you add for shielding is a kilogram your propulsion system has to accelerate to a big fraction of light speed, then decelerate again. So as you increase shielding to survive dust impacts and radiation over millions of years, you raise the energy bill and the fuel requirement, which pushes the mission deeper into the realm of fantasy. To make space safe, you turn your ship into a giant rock, and to move that rock fast enough, you need a level of power that no realistic civilization can spare for a single journey. So you end up in a nasty trade-off. How do you choose between going slower with less damage and going faster with more armor, when each choice makes some other problem explode? If you decide to go slower, maybe 1% of light speed instead of 10%, dust impacts are less violent, and you can get away with less armor. The problem is your travel time goes up by a factor of 10. A 10 million year trip becomes a 100 million year trip. All the issues with multi-generation life support, social stability and hardware aging get worse by the same factor. Slowing down makes the outside universe less violent, but stretches your exposure time, so tiny failure probabilities grow into near certainties. If you go faster, toward 10% of light speed or more, you cut the travel time. But the kinetic energy of every dust grain hitting your hull goes up sharply, because the impact energy grows with the square of the speed. Double the speed, and the destructive energy does not just double, it jumps by 4 times. At 10% of light speed, even microscopic particles hit like bullets. At higher fractions, they hit like bombs. To survive that, you need armor that is not just thick, but absurdly thick, plus some active protection system constantly zapping or deflecting incoming particles. You're forced to pick your poison, crawl slowly through a milder storm for much longer, or blast quickly through a far deadlier storm that needs insane defenses. So maybe you try to cheat the trade-off with clever tech, with smart materials and fleets of tiny repair robots crawling over the hull, constantly fixing every little scar and crack as it appears. Does that finally give you a safe path through this minefield? Self-repair sounds powerful on paper. Nanobots or micro-robots patrolling the ship, filling in pits, replacing damaged panels, swapping out burned electronics. In reality, every repair system is just another layer of stuff that can break. The repair robots are also made of atoms, also vulnerable to radiation, dust and wear. Their control software also suffers from random bit flips and gradual corruption. Over a few decades, automated maintenance could help keep a ship healthy. Over millions of years, you are running an endless race against entropy, with your tools degrading while they try to fix everything else. You also have to think about the deeper failures, not just dents and scratches. A big dust impact that punches through the outer armour could take out entire sections of your repair infrastructure in one shot. A series of radiation spikes could flip bits in your control systems, making the repair swarm itself malfunction. Now you're not just fixing hull plates, you're fixing the things that fix the hull plates and fixing the things that manage those in a nested chain that can collapse at any weak link. After enough time, the probability that some combination of hits and failures knocks out critical repair capacity creeps toward 1. So the intergalactic road is not a clean, empty shortcut. It is thin gas, dust and radiation stretched over millions of light years, and at the speeds you need for any meaningful trip to Andromeda, that almost nothing behaves like a constant attack. To survive, you either move slowly and accept crushing time, or move fast and accept crushing shielding and repair demands. Neither path feeds back into the problems you already saw with rockets, energy, and human lifespans. And even if you somehow protected your ship perfectly against all that, sealed it like a moving fortress, there is another layer of reality waiting for you, where time itself stops behaving the way you expect once you push close to light speed, and the rules of relativity start to twist your whole idea of a journey. So after all the brutal time and distance we have talked about, the obvious question is, doesn't relativity give you a cheat code? If time slows down for fast travellers, can't you just lean on that and skip the worst of the trip? Special relativity really does say that at speeds close to light, time on your ship runs slower than time in the outside universe. If your ship is cruising at around 99% of light speed, people on board age much more slowly compared to people back on Earth. The factor is big, not tiny. At about 0.99 times light speed, your clocks tick roughly 7 times slower than clocks in the rest frame, the frame of the galaxy you left. So if the outside universe says the journey takes 10 million years, people on the ship might only experience around 1.4 million years. That sounds like a big win. It cuts the subjective travel time by a factor of 7. The problem is, you are still sitting at over 1 million years from the ship's point of view, and millions from everyone else's. Time dilation softens the blow. It does not turn a journey to Andromeda into something a human or even a long-lived species can casually do. So then the real challenge becomes obvious. If time dilation only kicks in hard near light speed, how do you actually get a real ship with real people all the way up to 99% of light speed without destroying them on the way? To reach that kind of speed, you need enormous amounts of energy, but you also need to think about acceleration, the rate at which you change your speed. Humans can handle around 1 g of constant acceleration pretty well, about 9.81 meters per second squared, roughly 32 feet per second squared. That is what you feel standing on Earth. If your ship accelerates at 1 g, people inside feel like they are standing on a floor with normal gravity. That is actually nice for long trips, no weightlessness health issues, but with that gentle acceleration it still takes a long time to ramp up to 99% of light speed. You're talking months to years of continuous thrust just to speed up, then you have to flip the ship around and spend months to years slowing down at the end, otherwise you blast past Andromeda and head into deep space. If you try to shorten that time by cranking the acceleration up, you start pushing the crew into dangerous G levels. At 3 or 4 g for long periods, the human body struggles, blood flow is affected, organs are stressed. Fighter pilots can handle brief bursts of high G with special suits and training, but not months of it. So to keep the crew alive and conscious, you're basically locked into accelerations around 1G or less, which means there is no fast ramp to near light speed. The climb itself becomes a major part of the mission, burning through fuel or energy reserves constantly, long before you even get to cruise. That leads to the next punch from Relativity, which is not just about time, it is about how violently the energy requirements explode as your speed creeps closer to light. At low speeds, the kinetic energy of a moving object increases roughly in proportion to the square of your speed. So if you go twice as fast, you need about 4 times as much energy. As you approach light speed, special relativity adds an extra multiplier, a factor physicists call the Lorentz factor. This number starts at 1 when you're at rest and climbs higher as your speed increases. At 99% of light speed, that factor is around 7. At 99.9%, it jumps to around 22. Each extra 9 in that percentage makes the factor skyrocket. What that means in plain language is, the closer you get to the speed of light, the more brutally expensive each extra bit of speed becomes in terms of energy. Going from 10 to 20% of light speed is already 4 times the energy. Going from 90 to 99% is far, far worse than just adding 9 more percent. The universe heavily punishes the idea that 99% of light speed is just a bit faster than 90%. Even if you swallow that and say, fine, it is expensive, we will pay the energy cost because we want that time dilation, you then run into a different kind of time problem. Whose time are you actually helping? Time dilation mostly helps the travellers. On board the ship, clocks tick slower and people age less during the trip. If your ship's timeline is compressed to, say, a few 100,000 years, while the outside universe runs through millions of years, that is a relief for the crew. But from the point of view of Earth, or whatever homeworld launched you, those millions of years still pass. Continents move, climates swing between hot and cold, ice ages come and go. Civilizations rise, collapse, and maybe vanish entirely. Languages mutate into new ones, then into others. Tech levels climb, crash, and reset. By the time your ship reaches Andromeda and slows down, the society that built it is almost certainly gone or unrecognizable. There may not be any culture left that remembers you left. So yes, Relativity lets the people on the ship say, we only spent this many years travelling, but for everyone else, the mission is functionally lost in deep time. From the home civilization's point of view, it might as well be impossible. And underneath all of this is the one rule Relativity never lets you bend. No matter how much energy you throw at it or how cleverly you design your engines, you never actually reach light speed. In special relativity, any object with mass needs more and more energy to go faster. As its speed approaches the speed of light, its effective inertia, its resistance to being accelerated, climbs without bound. To push a massive object all the way to light speed itself would require infinite energy. There is no trick fuel, no advanced engine, no alien technology that can change that basic rule, unless you literally change the structure of space-time itself, which is a different conversation. As long as you're talking about rockets and engines that push en masse in normal space, you're locked out of light speed. You can get close, you can enjoy some time dilation, but there is a hard ceiling, and that ceiling is exactly what makes the Andromeda problem so vicious. You can never make the outside travel time drop below 2.5 million years, because that is the light travel time. You can only play with how much of that your crew feels. So Relativity gives you one small gift. Your own clocks can run slower if you are willing to spend an insane amount of energy to get close to light speed. But that gift comes with sharp claws. The acceleration phases are long and dangerous. The energy requirements grow to absurd levels. The home civilization still ages millions of years, and the speed of light stays as an absolute limit you cannot cross. Even with the most extreme use of relativity, Andromeda does not turn into a practical destination. It just turns into a slightly less hopeless one from the traveller's narrow point of view. And this brings up the next question. Even if you somehow pushed a ship into that regime, flirting with light speed, soaking up radiation, surviving particle hits, and fighting the energy costs, what about the ship itself? Can any material structure you build today or in the near future actually hold together under constant stress, impacts, and thermal cycling for millions of years of flight? How long do you actually expect a machine to stay in one piece? Not working for a few years, but holding together for 1,000,000 years or more. For an Andromeda run, every physical part of your starship has to survive that kind of timescale. Every weld, every joint, every beam, every pressure vessel sits under constant stress. The hull heats and cools as systems turn on and off, as the ship rotates, as it passes through different radiation environments. Metals slowly creep under stress. They deform even without breaking. Tiny cracks build up from vibration and thermal cycling. Polymers slowly outgas in vacuum, losing plasticizers, becoming brittle and cracking. On Earth, bridges, planes and power plants need inspection and repair after a few decades. Your intergalactic ship is that kind of structure, but left in hard radiation and vacuum with no outside help for geological ages. You might say, that is fine, you will just maintain it. But what happens when the environment you're flying through is actively trying to punch holes in your hull again and again at violent speeds? Once you push up to around 10% of light speed and beyond, the dust problem becomes a material problem you've never solved before. A tiny grain of interstellar dust, something the size of a sand grain, hitting your hull at that speed, carries kinetic energy in the range normally associated with high explosives. Each impact blasts material out of the surface, creates shock waves in the structure, and sends fragments spraying inward. In labs, you can fire projectiles at plates and see how they behave, but those tests cover limited speeds and only a small number of shots. You do not test for continuous relativistic micro-impacts over millions of years. To handle that, you would need hull materials that can absorb those hits, self-seal, and not accumulate fatal damage. You would need layered shields, sacrificial bumper layers, maybe electromagnetic fields up front to deflect charged particles. None of that has been tested even for 1,000-year cycles, let alone million-year ones. And every defensive layer you add connects back to the earlier problems. More mass to accelerate, more structure that can crack, more surfaces that can be eroded. Even if you assume somehow the basic hull survives the hits, you still have to deal with heat, because nothing in your ship runs at zero power, and in space getting rid of energy is always harder than generating it. Your reactors, life support, computers and lighting all turn input energy into output work plus waste heat. On Earth, you throw that heat into the air or water and it spreads. In vacuum, there is no air. The only way to dump heat is by radiation, shining it away as infrared light from large radiator panels. These panels have to be big, thin and exposed to be effective. Over millions of years of operation, those radiators must survive micrometeoroid hits, corrosion from any residual atomic oxygen in some regions, and constant temperature cycling as power usage goes up and down. If a radiator panel is punctured, its coolant might leak out. If too many panels are lost or damaged, your ship slowly overheats. Electronics fail faster, life support systems struggle, living areas turn into slow ovens. On the other side, if a control fault makes the cooling too aggressive, sections could drop to damaging low temperatures. A single unrecoverable failure in thermal management is enough to end the mission, and you need to avoid that not for a few years, but for spans longer than any civilization has so far existed. So even if your structure and your cooling keep up, can your control systems and electronics really run for that long, under constant radiation and stress, without eventually degrading beyond repair? Electronics are one of the most fragile parts of modern technology. Semiconductors rely on precise doping levels and tiny structures. Radiation gradually knocks atoms out of place in those lattices, changing their behavior. High-energy particles flip bits in memory and logic, causing random errors. On Earth, we are comfortable with phones, laptops, and servers that last a few years, maybe a decade. Industrial and space-rated electronics are tougher, but even then you design for missions lasting maybe 10 to 20 years, not 10 million. For Andromeda, you need either electronics that do not just last a long time, but can be rebuilt over and over. That means onboard manufacturing to produce new chips, new boards, and new sensors from raw materials, along with enough knowledge and tooling to keep that industry running while the original engineers are long dead. You need fault-tolerant computing architectures that can handle constant random errors without falling over, with heavy redundancy and self-checks. That increases complexity, and complexity gives you more ways to fail. Over enough time, some accumulating combination of minor flaws, design limits, and random damage is going to push parts of the system outside their safe envelope. At this point, you might look for comfort in our history of big, long-lasting structures. Maybe you point to monuments and ancient buildings that have stood for thousands of years and say, "See, we can build things that last." That is where the last reality check in this section hits. The oldest major human structures, things like the pyramids in Egypt, are roughly 4,000 to 5,000 years old. They are piles of stone, not active machines, and even they erode, crack, and need modern stabilization. Mechanical systems struggle to survive even a century without focused maintenance, and that is sitting still on Earth. We have no real data on any complex machine being left to operate in a harsh environment for 10,000 years, let alone 100,000, let alone a million. Long before that, lubricants break down, seals dry out, metals corrode, plastic parts crumble, and designs that look solid in year 1 are dangerously worn in year 500. To bet an Andromeda mission on future materials is to assume not just one breakthrough, but a whole stack of them. You need metals that do not fatigue under endless cycling, composites that do not outgas in vacuum, radiation-hardened electronics with self-repairing logic, self-healing hulls that can swallow repeated high-energy impacts, and radiators that never leak or clog. Then you have to test all of that for the equivalent of 1,000,000 years of abuse, which is basically impossible in any realistic lab setting. You have to trust your models and simulations completely, because you will never have the time to run a full-duration test. If those models are wrong in any important way, the failure shows up when the ship is already centuries or millennia into the void. So the material story lines up with everything else you have seen so far. The distances are too large, the timescales too long, the speeds too extreme, and the environment too hostile for any structure remotely like the ones you can build today to stay intact and reliable, all the way to Andromeda. The best materials you have now are designed for decades. This mission demands durability on the scale of mountain ranges and tectonic plates, and that is not what human engineering does. And even if you somehow claimed you could build a ship that holds together that long, that keeps its structure, its cooling, and its electronics running, you still have the problem that the thing you are aiming at is not sitting still. The galaxy you want to reach is moving, its stars are drifting, and space-time itself is warped and shifting under everything, which turns navigation over millions of years into its own nightmare. You might think navigation is the easy part. You point the nose at Andromeda, lock in a straight line, and let the engines do their thing. The problem is, there is no fixed Andromeda to aim at. Andromeda is moving toward the Milky Way at about 110 kilometers per second, roughly 250,000 miles per hour. The Milky Way itself is also moving, orbiting the center of a mass of the local group. On top of that, the whole local group is falling through the larger cosmic web, pulled by the gravity of galaxy clusters and dark matter. So when you say aim there, what you really mean is aim at an object that will be somewhere completely different by the time you get anywhere close. If your trip takes millions of years, then by the halfway point the target has shifted drastically from the coordinates you started with, and the starting line has moved too. So you adjust your thinking and say, fine, I will just aim for the general region, somewhere inside Andromeda's disk. Does that fix it? No, because the galaxy itself is not a rigid target either. It is a swarm of moving stars. Inside Andromeda, individual stars orbit its center at hundreds of kilometers per second, similar to or a bit faster than stars in the Milky Way. Picture that in numbers. A star might be doing 200 to 300 kilometers per second around the galactic center. That is 450,000 to 670,000 miles per hour. Over millions of years, those orbits wrap around many times. Stars drift up and down through the galactic plane, spiral arms shift. clusters form and dissolve. If you say, "We want to arrive near that one sun-like star over there," you are trying to intercept something that has traced out a long, complex orbit by the time you get near it. You are not flying toward a fixed starport, you are trying to meet a specific grain of sand in a storm of hundreds of billions of grains, all moving in a three-dimensional gravitational dance. So now your navigation problem is not just where is Andromeda, it is where will some tiny specific piece of Andromeda be in 3 or 10 million years, given everything else that is also moving and tugging on it. That means your ship needs a map, but not a static one. Your map has to update for millions of years, tracking how gravity reshapes everything. Gravity does not just pull in simple straight lines, you have stars tugging on other stars, whole gas clouds moving, satellite galaxies orbiting and being stripped apart, plus a huge dark matter halo you cannot even see directly, only infer from its effects. Small errors in your initial picture of where the mass is or in how fast something is moving grow over time. Over a few years, those errors are small. Over 1,000,000 years, they can become huge. It is like taking a very long billiard shot on a table that is itself slowly bending and warping while the balls roll. Even if you start with excellent measurements, chaotic effects and tiny uncertainties multiply until your prediction is off by light years. To keep the course accurate, your ship would have to constantly measure its surroundings, refine its model of the local gravitational field, and adjust its trajectory. That is hard enough on solar system scales. On intergalactic scales, you're adding the complexity of dark matter, galaxy clusters, and long-range gravitational pulls from massive structures that are mostly invisible. And that brings up another layer, the fact that space itself is not flat when you step back and look at this distance. On these huge scales, you cannot treat space as a simple flat grid. General relativity says mass and energy warp space-time. Galaxy clusters and dark matter halos create curved regions where light rays bend and paths that look like straight lines in normal thinking are actually curved geodesics in space-time. Your starship's trajectory is not just a straight arrow you draw on a map. It is a path through curved space-time, affected by everything from nearby galaxies to large-scale structures. To really optimize that path, to save fuel and avoid unexpected deflections, you have to understand where the mass is and how it is moving, not just now, but across the whole duration of your trip. You only ever see that mass configuration in the past, because all your information comes from light that took millions or billions of years to arrive. You are plotting a route using old snapshots of a landscape that keeps shifting. You might respond, "All right, the math is ugly, but surely we could just keep talking to the ship, send updates, send better maps as our telescopes improve back home. That would at least fix some of the long-term errors, right?" That is where distance kills you again, but this time in communication instead of travel. At the scales we are talking about, there is no such thing as real-time control. If your ship is halfway to Andromeda, it is about 1.25 million light-years away. A radio signal from Earth, moving at light speed, takes 1.25 million years just to reach it. The reply takes another 1.25 million years to come back. Any update from mission control arrives long after the conditions it was meant to fix have changed. By the time your home civilization knows there is a problem, the people, if any, on that ship are long dead, and the ship itself could have drifted somewhere completely different or failed entirely. So navigation cannot depend on regular guidance from home. It has to be fully autonomous for the entire mission duration. The ship's systems must discover errors, update charts, adjust course, and handle emergencies without any outside help, not for a few years like a Mars rover, but for millions of years. No uplink, no real-time override, no call Houston. Every software bug that slips through design, every subtle flaw in the navigation algorithms, every unanticipated configuration of mass along the way has to be caught and fixed by the ship itself, or it simply accumulates and pushes the mission off target. You're trusting a stack of code and hardware to stay sane and accurate on timescales that erase mountain ranges. Put all of this together and you see the pattern again. The galaxy you are chasing is moving. Its stars are drifting. The gravitational landscape is changing. Space-time is curved. Your maps are always old by the time you get them. And the only system allowed to make corrections is trapped on the ship without any possibility of fast conversations with home. Navigation stops being a matter of precise math and turns into a long fight against chaos, with tiny errors waiting millions of years for their chance to ruin you. And even if you somehow solved that, even if your autonomous navigator drove a perfect line across curved space-time to a moving target, there is one last large-scale problem waiting for you that is not about motion at all. The universe itself is expanding underneath every route you try to draw, and beyond your local neighborhood, that expansion quietly makes most of the cosmos unreachable in principle, no matter how clever your ship is. You keep hearing that the universe is expanding and it sounds like background info, a trivia fact that doesn't really affect whether you can point a ship at Andromeda and go. The truth is, on the larger scales, expansion is not background. It is the stage itself. Galaxies are receding from one another because space between them is stretching. Astronomers describe it with something called the Hubble constant, roughly 70 kilometers per second of extra recession speed for every megaparsec of distance. 1 megaparsec is about 3.26 million light years. So add another 3.26 million light years, space adds another 70 kilometers per second of separation. That's about 43 miles per second between you and some distant galaxy, just from the expansion alone. Now, inside our local group, gravity is strong enough to beat that stretching. The Milky Way and Andromeda are gravitationally bound. They are actually moving toward each other, on a collision course in about 4 to 5 billion years. That is why Andromeda is not drifting away like most other galaxies. But step outside this small neighborhood, and expansion wins. The farther out you look, the faster galaxies recede, not because they are flying through space like bullets, but because space itself between you and them is stretching. Any attempt to go not just to Andromeda, but beyond it, into truly deep intergalactic space, has to fight this background expansion, and past a point, you simply cannot. So how far out does that barrier sit? And how bad does it get for anything trying to chase the rest of the universe? There is a distance called the cosmological event horizon. Beyond that, galaxies recede from us faster than light, again not because they are breaking physics locally, but because there is so much expanding space in between that their total recession speed exceeds light speed. You can still see some of them today because their light left long ago when they were closer, but from now on any signal they emit will never reach us, and any signal we send will never reach them. They are outside our future light cone, effectively cut off forever. Now think about what that means for a starship. No matter how good your engine is, as long as you are moving through space locally at less than light speed, you can never catch up with an object that space itself is carrying away faster than light. You can run as hard as you like along the treadmill, but the treadmill length keeps stretching under your feet faster than you can move. There is no clever route, no slingshot, no special fuel that changes that. Those galaxies are not just very far, they are unreachable in principle, not just in practice. So why even talk about Andromeda if most of the universe is already drifting beyond reach? The answer is Andromeda is special, and that is exactly what makes the situation feel worse, not better. Andromeda is part of our local group, locked into the same small gravitational bubble as the Milky Way and a few dozen dwarf galaxies. Because of that, it is not being carried away by expansion, it is coming closer. In a few billion years, the Milky Way and Andromeda will merge into one larger galaxy. That sounds friendly, like a neighbour you will definitely meet one day whether you want to or not. But look up at almost every other bright galaxy in the night sky, and the story changes completely. Those galaxies are receding. Many of them are already beyond the distance where a signal sent today could ever catch up, even if that signal were light itself. So when you say, let's go to Andromeda, you're already picking one of the few major galaxies that are, in principle, not lost. And even then, everything we've talked about, distance, energy, materials, lifespans, makes it practically unreachable. Andromeda is like the last friendly island before an endless ocean of places that, on paper, you can never sail to at all. And this barrier is not static. It is not like there is a fixed horizon and it just sits there. The really unsettling part is that the boundary of what is reachable is moving in the wrong direction over time. Observations of distant supernovae and the cosmic microwave background show that cosmic expansion is accelerating, not slowing down. The driver of that acceleration is what we call dark energy, some kind of energy built into space itself that pushes galaxies apart faster and faster as the universe grows. As that acceleration continues, more and more galaxies cross over that event horizon and slide into the permanently unreachable zone. The longer a civilization waits to launch missions to far-off galaxies, the fewer possible targets remain in principle. You are living in a cosmic era where you can still see an enormous number of galaxies, but over future billions of years, many of those visible islands of light will drop out of causal contact. Their light will still be in your sky, but any attempt to go there, even at light speed, will fail because the space in between is expanding too quickly. The available playground shrinks with time, even while your telescopes still show a rich universe. So where does that leave Andromeda itself, sitting there in the local group, apparently safe from expansion, yet still completely punishing as a target? Because Andromeda is gravitationally bound to us, a trip there does not break any expansion rules. Space between the Milky Way and Andromeda is not stretching fast enough to block you. In strict physics terms, if you had insane amounts of energy, absurdly durable ships, and a way to keep a moving civilization alive for millions or tens of millions of years, you could launch something and get it there. Expansion does not forbid that. But here is the key point. All the things that make most galaxies unreachable in principle, finite light speed, accelerating expansion, enormous energy demands, are already enough to crush you long before you even step outside the local group. You do not need a distant, receding target to hit an impossible wall. The nearest big galaxy, the one that is actually coming toward you, already forces you into ridiculous travel times, impossible energy budgets, lethal radiation environments, material limits, and navigation problems across moving curved space-time. So Andromeda is not just a destination, it is a demonstration. It is the easiest intergalactic target you will ever have, and it still needs engineering, biology, and power control so extreme that it might as well be magic. If the nearest neighbour is effectively out of reach, then the idea of hopping from galaxy to galaxy across an expanding universe collapses completely. The frontier does not go on forever in any practical sense. It slams shut just beyond your local group of galaxies, and everything beyond that becomes scenery only. And even inside that small reachable bubble, even if you pretend you can somehow pay the energy bill, build unbreakable ships, and thread the moving cosmic maze, you still face one more brutal requirement. You have to carry a working, self-contained Earth with you and keep it alive, stable and sane for as long as you are out there. You think you are designing a spacecraft, but for Andromeda, you're actually being asked to design a tiny artificial planet that has to work for longer than any real civilization has ever existed. Humans need steady gravity, either from a big rotating ring that simulates 1g with spin, or from constant acceleration. You need breathable air with the right oxygen and nitrogen mix, clean water cycling forever, food grown on board, and a way to handle every kilogram of waste without dumping it overboard. You also need spaces that do not drive people insane, places to move, to be alone, to raise children, to have some sense of normal life. On Earth, all of that is supported by an entire biosphere wrapped around a planet 12,700 kilometers wide, about 7,900 miles. On an Andromeda ship, you are trying to compress the same functions into maybe a few cubic kilometers of metal and machinery, a few cubic miles, and then demand that it keeps working for millions of years. So how stable are closed systems when humans actually try to build them? and what happens when you stop having a whole planet as a safety net. Experiments like Biosphere 2 showed how fragile closed ecologies really are. A small group of people lived inside a sealed habitat with soil, plants, animals, and recycled air and water. It was supposed to run mostly on its own, like a mini-Earth. Instead, oxygen levels dropped, carbon dioxide spiked, some species died out, and the team had to intervene from outside to keep things going. That was over a period of months to a couple of years, not thousands of years, not millions. On your Andromeda ship, you cannot call for outside help. If your oxygen slowly starts dropping or some key plant species crashes, you cannot truck in fresh soil or swap out a broken piece of hardware from a factory on Earth. The real problem is that every cycle, carbon, nitrogen, water, minerals has to be perfectly balanced. Plants have to absorb enough carbon dioxide and release enough oxygen. Bacteria in the soil have to break down waste at the right rate. Nutrients have to flow through crops, people, and back into the system without subtle losses. Over long times, even tiny imbalances accumulate, and a system with no external input will drift. One small error in how you design the ecology, one species that thrives too much or too little, can start a chain reaction. In a few years, you get stress. In a few centuries, you get collapse. In a million years, if you have not engineered constant corrections, the odds are completely stacked against stability. And even if you get the big cycles roughly right at the start, what about the invisible players, the microbes that live on every surface and in every drop of water? Bacteria and other microbes reproduce on timescales of minutes to hours. Over a single human lifetime, they go through tens of thousands of generations. Over millions of years, they go through billions. That means evolution for microbes happens at a speed that makes human genetic change look frozen. Inside your ship, in your pipes, your air filters, your soil, your storage tanks, you are seeding a whole new microbial universe. Some of those microbes will find ways to eat your sealants, your plastics, your metals. Some will form biofilms, slimy layers that clog pipes and protect bacteria from cleaning chemicals. Some will adapt to your disinfectants and medications, becoming resistant. The ecosystem you carefully designed at launch will not stay the same. Microbes will shift the balance. Maybe a certain bacteria blooms and strips oxygen from water, or generates toxic byproducts in your air. Maybe a plant pathogen evolves and wipes out your staple crop. Maybe a slow, creeping corrosion process driven by some strange microbe starts eating your reactor coolant lines. To stay alive, the crew has to constantly monitor and control not just visible plants and animals, but microscopic life on a ship-wide scale, correcting for evolutionary changes that never stop. Over millions of years, you are running a never-ending biosecurity operation in a closed can, with the enemy evolving faster than you do. All of that workload assumes one more thing, that your power source never fails, because every part of your life support depends on steady energy. So what do you use and how long must it last? If you rely on a compact reactor, fission or fusion, that system has to operate or be rebuilt again and again for periods far beyond anything human engineers have planned for. Today's nuclear reactors are designed for a few decades of service, maybe extended with refits. For an Andromeda mission, you do not need 30 or 40 years of uptime, you need thousands, millions, with no chance to shut everything down and bring in a replacement from a shipyard. If you push for a fusion drive and power plant, you need a machine that holds and controls plasma at hundreds of millions of degrees, constantly, with no major leaks or breakdowns, for longer than Homo sapiens has existed. If you try to lean on solar energy, you face a different set of limits. Solar panels only work well when you're close to a star. In the deep void between galaxies, starlight is faint and scattered, so you would need enormous collecting areas to get meaningful power, and those panels degrade under radiation and particle hits. You also have to manage your flight path relative to stars, maybe diving near them to recharge, which adds navigation complexity and risk. In every scenario, whatever power plant you choose must effectively outlive entire civilizations. It must be repairable with materials you can mine and refine on board, and its failure modes must be gentle enough that the crew gets time to fix problems before they become fatal. Then comes the most unforgiving truth about life support in deep space. There is no backup location, no spare habitat, no second chance if something big goes wrong. On Earth, if one region suffers famine, pollution or disaster, people can move, aid can flow in from other regions, and the planet's total biosphere cushions the impact. On a ship, you have one environment, one set of farms, one core water recycling loop, one air system, one microbial ecosystem, whether you like it or not. If your main crop fails because of a disease or a genetic problem, you cannot just divert shipments from another continent. If some contaminant quietly builds up in your closed water cycle and reaches toxic levels, you do not have fresh rivers and aquifers to draw from. If a key pollinator species dies out, your food production does not have wild ecosystems to fall back on. A single unfixable contamination event in your hydroponic systems, one major leak in your main water reservoir, one runaway reaction in your air scrubbers, can move your life support from recoverable crisis to slow, unstoppable death. The people on that ship will feel it as air that gets a little harder to breathe, crops that start to yield less, illnesses that become more common, and then a point where there is nothing left to repair because the underlying ecological base is gone. Your Andromeda mission ends not with a dramatic explosion, but with a few last breaths in a dark metal shell that still technically exists, still coasts through space but can no longer support human life. So when you zoom out, life support for an Andromeda trip is not a side problem, it is the core problem. You're trying to compress Earth's biosphere, its geology, its water and air cycles, and its energy flows into a box, then demand that this box stays balanced and functional for timescales that normally erase species. Every flaw, every drift, every unexpected evolution has millions of years to grow into a mission-ending failure. And even if you somehow convinced yourself you could do all that, pressurize a tiny Earth, power it forever, hold its structure together, and keep its people and microbes under control, you still have to ask how you even get the resources, the will, and the long-term stability on your home planet to build such a thing in the first place and keep supporting the project across generations. At this point, the problem stops being just physics and engineering and turns into something harder. You have to get an entire civilization to act like one focused mind for longer than any empire has ever lasted. Building a ship that can even attempt Andromeda is not a national project, it is a planet-level project. The mass of the ship, the energy you need to build and fuel it, the factories, the research, the testing, all of that together rivals or exceeds everything humanity is doing right now across all industries. You would need a stable, coordinated global civilization that can stay on task for thousands of years just to design, test and build this thing. And that civilization cannot afford major collapses, world wars, or radical shifts in priorities halfway through. One serious breakdown in global cooperation and the project stalls, or the knowledge you need is lost, or the will simply evaporates. So even if you could, in theory, organize the planet once, how do you convince generation after generation to keep paying for a mission that will not help them personally at all? Economics absolutely hates the idea of pay now, get something in 10 million years. Every kilogram of steel you put into an Andromeda ship is a kilogram you did not use for buildings, hospitals, power plants, or defences back home. Every gigawatt of power you push into your giant shipyard or your propulsion test range is power you are not using to run cities, cool a warming climate, or feed people. Real economies work with discounting. Future benefits are always valued less than present ones. The further out the payoff, the less anyone wants to pay for it. Here, the payoff is so far out that for all practical purposes, it is zero. No voter, no investor, no government in any recognizable form gets anything back. They are being asked to pour planetary GDP into a project whose reward lands so far in the future that even their species might have changed or vanished by then. To keep that investment flowing year after year, century after century, you would have to somehow override basic economic behaviour and build a culture that accepts permanent sacrifice for a goal literally no one alive will see completed. And that runs straight into the next human problem. Your culture does not stand still either. It mutates on timescales much shorter than any Andromeda timeline. Look at how fast values shift now. In a few decades, ideas that were normal become unthinkable, and vice versa. Systems rise, fall, and get replaced. Identities change. Decision made in the 25th century to build an Andromeda ship might look noble and visionary to them, but by the 30th century, people might see it as a gigantic waste or even as a crime, trapping thousands of future humans on a forever mission they never chose. By the 100th century, if humans are still around, they might have totally different priorities, different ethics, different tech. Expecting them to keep honouring a plan launched thousands of years earlier is optimistic to the point of fantasy. Across such long spans, you also have to worry about sabotage, corruption, and simple boredom. A project this big unavoidably creates huge concentrations of power and resources. That attracts people who want to divert it for their own goals. One regime might freeze funding, another might try to weaponize the tech, another might shut it down entirely because it clashes with their belief system. Keeping a multi-millennial commitment to a single mega project without interruption is, in practice, harder than building any engine. And even if you get past that and manage to launch the ship, the problem does not end at the pad. It just splits into two civilizations, one on Earth and one inside the ship. Once the ship leaves, the people on board are cut off in every meaningful way. They form their own society, with their own language shifts, their own traditions, their own conflicts, their own stories about why they are there. The original mission profile written back home becomes an old myth to them after a few generations. After 1,000 years, they may still respect it. After 100,000, they may reinterpret it. After 1,000,000, it is anyone's guess. At some point, the ship's population might decide the mission no longer makes sense. They could choose to slow down and live in intergalactic space, turn back toward the local group, or repurpose the ship as a permanent wandering habitat. From Earth's side, you cannot enforce anything. You have no real-time communication. You have no control. The moment the ship leaves, it becomes its own unit, with the power to change its own destiny in ways that completely ignore what some ancient planners on a distant planet wanted millions of years ago. And here is the big, awkward question that hangs over all of this. If your civilization is actually capable of doing everything we are talking about, why would you even want to leave on this scale? To build a viable Andromeda mission, you must have already solved problems like global energy production at massive levels, climate control, resource recycling, and large-scale social coordination. You must be able to run closed ecosystems, protect billions of people from environmental collapse, and keep technology and infrastructure stable over huge spans of time. Those same abilities could be used to make life in your home system and your home galaxy extremely good. You could build habitats around stars, terraform planets, harvest energy with stellar-scale structures, and create vast virtual worlds. In other words, by the time you are technically ready to launch an Andromeda ship, you're also technically ready to turn your own region of the universe into something close to utopian. At that stage, the incentive to pour staggering amounts of material energy and attention into a single, ultra-risky, ultra-slow mission shrinks. Why send a tiny fraction of your people into a hostile void for millions of years when you can explore the universe remotely with probes and telescopes and make your immediate surroundings astonishingly rich and full? The more powerful you are, the less sense it makes to gamble that power on a project that has almost no payoff compared to what you could do locally. So from the civilization point of view, Andromeda is not just hard, it is misaligned with how human societies actually behave. You need global unity without interruption, economic sacrifice without return, cultural stability without drift, and a willingness to spend godlike capabilities on a mission that benefits almost no one. And even if you somehow line all of that up, physics still sits there at the end with one last quiet rule. No matter what you do, everything breaks, order decays, and the longer you push against that, the more the odds tilt against you. You can sum up a lot of what's wrong with an Andromeda mission in one sentence. Everything breaks if you give it enough time. That is not just pessimism, it is the second law of thermodynamics. Entropy increases. Ordered systems tend to drift toward disorder unless you constantly put in energy and work to push them back. On short timescales, decades or centuries, you can win lots of local battles. You can keep a station running, a city working, an ecosystem in balance. On a finite closed starship running for millions of years, that same rule turns into a wall. To hold a complex, high-tech, life-supporting system together, you have to constantly move energy through it, constantly repair, clean, refine, and reorganize. Over that much time, fighting entropy stops being a maintenance task and becomes the main job. Every other goal, including get to Andromeda, gets pushed into the background behind keep the ship from slowly falling apart at every level. So start with the most obvious layer of order you're trying to preserve, not the hardware, but the information that tells you how everything works and why you're doing any of this in the first place. Your navigation charts, your star catalogues, your detailed maps of the Milky Way and Andromeda, your engineering schematics, your medical knowledge, your cultural archives, your laws and history, all of that lives in physical media. It might be printed, etched, or stored in digital memory. In every case, entropy pushes on it. Cosmic rays flip bits in memory cells, storage media slowly degrade, magnetic domains drift. Even if you have good error correction, that only works if the correction codes themselves are still valid and the checking hardware is still working correctly. On top of that, humans keep rewriting their own data. Coding standards evolve, languages change, formats get updated. Old files become unreadable because the software that understood them is gone. If you do not have continuous intelligent curation, people whose job it is to check, migrate, translate, and verify the core knowledge base, it starts to rot. Now stretch that not over decades but over tens of thousands of years. At some point, the original schematics for your reactor or drive system might exist only in corrupted fragments, or in a language nobody can fully interpret. The story of why the ship launched might turn into a simplified tale, then into legend. After enough millennia, the descendants on that ship may not just have lost some technical details, they may have lost the entire plot. And while your information decays, your physical systems are also marching through their own failure curves, each at its own rate. Every component on the ship has a mean time between failures, an average interval before it breaks. Pumps, valves, seals, circuit boards, bearings, hinges, sensors, all of them fail eventually. On a short mission, you carry spares, you schedule maintenance, and you're fine. On a million-year mission, every part will fail many times. You cannot store enough pre-made spares for that duration, because the spares themselves age in storage. So you build onboard factories to manufacture new parts from raw materials. Those factories have their own moving parts, their own control software, and their own failure curves. Very quickly, the maintenance problem becomes recursive. You're not just repairing the ship, you're repairing the systems that repair the ship, and the systems that keep the repair factories running, and the systems that manage the supply chains of raw materials and energy feeding those factories. That is a hierarchy of maintenance that grows more complex as you try to make it more robust. Over millions of years, cumulative wear, small design flaws, and unanticipated interactions between subsystems pile up. At some point, the total maintenance load outruns the capacity of your workforce and your automation. Something crucial misses an inspection, a hidden crack propagates, a production line drifts out of tolerance, and a failure slips through that you can't patch with the tools you have left. Entropy is not just attacking machines, it is also grinding away at the biology and the minds running the whole show. Human brains are not static memory chips. Neural connections strengthen and weaken with use. Memories distort. Myths and rumours mix with facts. Even if every generation on the ship tries to preserve the mission honestly, small misunderstandings creep in. Maybe a key procedure gets simplified for clarity and loses an important detail. Maybe a technical term gets misinterpreted and gradually shifts meaning. Multiply that by thousands of generations, each adding a small layer of noise. culture fractures too. Different sections of the ship might develop different traditions and beliefs. Some groups might become skeptical of the mission, others might glorify it. Over long enough time, you're almost guaranteed to see splits, schisms, and entirely new ideologies. The original Andromeda mission plan turns into a story told to children, then into a symbolic origin myth, then into something unrecognizable to anyone who was present at launch. The biological substrate also drifts. Genetic changes accumulate. Physical and mental traits shift under selection pressures you did not fully predict. The crew that arrives, if anyone does, may not think like you, may not share your priorities, and may not even agree that continuing the mission is a good idea. Put those layers together, and you see the core pattern. You're asking a finite, closed system to keep itself highly ordered in the face of constant microscopic and macroscopic assaults, and to do so indefinitely. Human engineering is very good at local temporary pushes against entropy. You build a bridge, it lasts for a century with maintenance. You run a data center, it stays reliable for a few years if you swap failing drives and update software. You run a city, it depends on constant repairs, constant energy flow, constant garbage removal. All of these are small victories carved out for short periods of time. An Andromeda mission, in contrast, demands that you extend those victories to an almost absurd timescale. You want machines, ecosystems, and cultures to stay functional, coherent, and pointed at a goal across eras that erase mountains and rewrite coastlines. Physics does not explicitly say this is impossible, but it gives you a very clear warning. Entropy always increases overall. You can buy time by spending energy and effort. You can build pockets of order, but the longer you push and the more complex the system, the more ways it has to fail. Everything we know about complex systems, ecosystems, economies, large software projects says they eventually drift, fragment, and collapse if you stretch them too far. So when you zoom out, Andromeda level travel is not just a problem of distance or fuel or speed. It is a direct collision between what the universe does by default, slow drift into disorder, and what you would need to do, hold a ridiculous amount of order together in one moving box for millions of years. That is why in practice you are not just going on a long trip, you are trying to hold back the arrow of time with finite tools, over and over everywhere without ever dropping the ball. And after all of this, you might feel tempted to look for a way to dodge the whole issue, to ask whether there is some exotic shortcut, warp drives, wormholes, teleportation, that lets you skip the distances, the timescales, and maybe even some of the entropy. The final twist is that when you look closely at those cheats, the universe still finds a way to say no. Once you've seen how bad normal rockets look for Andromeda, the next instinct is simple: skip the distance. Warp drives, wormholes, teleportation, they sound like ways to dodge all the ugly parts at once. The problem is, when you actually plug those ideas into real physics instead of science fiction, they move from magic solution to mathematical curiosity you cannot build. Start with the big fantasy everyone knows, the warp drive. The Alcubierre drive is a real solution to the equations of general relativity. On paper, it wraps a bubble of space-time around your ship, compresses space in front, stretches it behind, and slides the bubble along so that from the outside you move faster than light, while inside you feel almost nothing. That sounds like a perfect cheat code. But when you look at what kind of stuff has to exist to make that bubble, the whole idea hits a brick wall. The equations demand negative energy density, matter with properties opposite to anything you've ever seen, something that has negative pressure and would gravitationally repel normal matter instead of attracting it. Quantum field theory does allow tiny regions of negative energy density in very special setups, but always in microscopic amounts, for very short times. Nothing in any experiment has ever shown large, stable clumps of exotic matter that could shape space-time on the ship scales, let alone galaxy scales. So you have a metric that says, if you had this impossible material, you could do this impossible thing. That is not engineering, that is a giant if. Then you might say, alright, warp bubbles are too weird. What about wormholes? jump points that connect two distant locations directly. General relativity again says, yes, you can write down solutions that look like tunnels through space-time, with one mouth near the Milky Way and another near Andromeda. Walk in one side, walk out the other, and you never had to cross all the empty space in between. But the same problem appears again, and worse. If you want a wormhole to stay open long enough to be useful, instead of pinching off instantly, you need negative energy threading its throat. Without that, gravity collapses the tunnel faster than light can cross it. Even if you imagine you somehow provide that negative energy, the wormhole has to survive insane tidal forces and quantum instabilities. Any radiation falling in gets blue shifted, pumped to higher and higher energy, which can feed back on the geometry and cause the whole structure to snap shut. Anything trying to pass through could be shredded by those effects, so on the blackboard, wormholes are a thing you can talk about. In a real universe with quantum fields, fluctuations, and no known source of macroscopic negative energy, they look less like portals and more like extremely fragile traps. So you might try to lean on the small cracks in our current understanding, the quantum hints that something like negative energy can exist, and ask if those can be scaled up. The usual example is the Casimir effect. Put two very flat, neutral metal plates extremely close together, separated by a gap measured in nanometers, billionths of a meter. Quantum fields in that tiny gap behave differently than outside, and you can interpret the resulting force between the plates as coming from a region of slightly lower energy density, effectively a tiny pocket of negative energy relative to the surroundings. That's real, it's been measured. But going from that to a warp bubble or a stabilized wormhole is like saying, I can make a tiny spark, therefore I can ignite a star. The same equations do not simply scale smoothly from nanometer gaps in a lab to structures stretching light years. The Casimir effect gives you a clue that the vacuum is complicated, not a blueprint for piling up enough negative energy to push a starship. Every attempt to design a reasonable way to grow those tiny effects into something macroscopic runs into either absurd demands for matter and precision, or flat contradictions with other parts of physics. Then maybe you back off from bending spacetime and ask if there's a way to cheat at a smaller level, with teleportation, moving information instead of matter. Quantum teleportation is a real working protocol, but what it does is very specific. It lets you transfer the quantum state of one system to another distant system, using entanglement and classical communication. You do not send the original particle. You destroy its state at the source when you measure it, and you use the entangled partner plus a normal, light-speed signal to reconstruct that state at the destination. That means two things that kill the sci-fi version. First, you need to have already moved some matter to the far end of the receiver and entangled it with matter at the start. Second, you still have to send classical information from A to B, and that can never go faster than light. So there is no way to teleport a human to Andromeda without either physically shipping a prepared receiver there first, which is the same travel problem you started with, or waiting millions of years for classical signals to cross the gap. The teleportation itself doesn't outrun light. It just uses entanglement as a strange non-classical link in a process that is still bottlenecked by normal speed limits. At this point you see a pattern. The equations of physics leave little loopholes that look exciting, but when you ask, can any finite civilization actually exploit this? The answer quietly turns into no. The phrase not strictly forbidden by physics is a trap. It usually means, in a very narrow idealized model, if you assume away all noise, all imperfections, and give yourself access to ingredients nobody has ever seen, then the math doesn't immediately break. That is not the same as doable by real creatures on a real planet with real matter. Warp drives, traversable wormholes, mega-scale negative energy machines, they all sit in that gap. The equations do not completely ban them, but they demand conditions so extreme and ingredients so alien that they might as well be outlawed for any practical species. For Andromeda, that means your list of options is shorter than you want to admit. Normal rockets fail on fuel and energy. Advanced drives fail on the same physics, just a bit later. Exotic geometry tricks fail on the need for negative energy and stability you cannot get. teleportation fails on the speed of light. You keep trying to find a door around the problem, and every one of them turns out to be painted on the wall. And when you step back from your own ideas and look outward instead, at the whole sky and all the galaxies in it, you see one last piece of evidence. If any of these exotic shortcuts were really practical, if intergalactic travel was something advanced civilizations could actually pull off, the universe should look very different than it does right now, and it doesn't. So here's the uncomfortable mirror you have to look into. If going to other galaxies is possible, why doesn't anyone seem to be doing it? We scan the sky in radio, visible light, infrared, X-rays, gamma rays. We map nearby galaxies in detail. We look at far ones as faint smudges in deep surveys. In all that data, you do not see obvious signs of artificial structures spanning the gaps between galaxies. No bright chains of stations, no repeating patterns of beams, no weird straight-line features crossing intergalactic space. If intergalactic travel were even barely doable for a fraction of advanced civilizations, you would expect at least one obvious case somewhere in the billions of galaxies we can see. Some galaxy that looks clearly engineered, some corridor of activity carved into the void. Instead, you see normal astrophysics, natural structures, nothing that screams, someone is paving this road. So maybe you say, fine, maybe the traffic is subtle, maybe they stay quiet in between galaxies, but surely if anyone has truly mastered energy, they would light up their own galaxy in a way we could spot from here, right? That is where the Kardashev scale becomes another data point. A Type 3 civilization, one that uses a significant fraction of the energy output of an entire galaxy, should leave huge fingerprints. If you build enough Dyson spheres or swarms around stars capturing most of their light and re-radiating it as waste heat, your galaxy's spectrum shifts. You dim in visible light and glow more in infrared. You might also see unusual patterns, like large regions with starlight suppressed but still radiating heat. Astronomers have actually looked for this. Surveys scan thousands of galaxies for odd infrared signatures that could match galaxy-wide engineering. So far, nothing is a clear match. You find dusty star-forming galaxies, active black holes, all the usual natural suspects, but no obvious this entire galaxy is full of megastructures case. That doesn't prove nobody ever gets to Type 3, but it strongly suggests that if such civilizations exist, they're extremely rare or behave in ways that don't involve grabbing most of their star's energy in visible ways. Either way, the absence of obvious Type 3 examples tells you this. Even turning one galaxy into a fully controlled home base is not something you see happening everywhere. If even that step is rare, routine commuting to neighbouring galaxies looks even less likely. Then you might fall back to a softer idea. Maybe advanced civilizations don't bother with giant visible structures, but they still talk. Couldn't we at least hear someone, somewhere, and use that as proof that spacefaring life regularly reaches those scales? For decades, SETI projects have pointed radio telescopes at stars, at galaxies, at patches of sky, looking for signals that stand out from background noise. You can argue about sensitivity and coverage, but the basic result is simple. No unambiguous technological signal has been found. No repeating narrow-band beacons that clearly say someone is transmitting intentionally. That silence does not prove we are alone. It could mean intelligent life is rare. It could mean advanced civilizations do not use radio in obvious ways. It could mean they hide on purpose. But notice what none of those options support. None of them suggest that intergalactic travel is a normal, expected upgrade path, something lots of species eventually do. If the universe were full of civilizations capable of building giant Andromeda-class ships or fast intergalactic networks, some of them should spill detectable signals, at least occasionally. The fact that you do not see or hear anything that stands out in a very loud way supports the idea that hitting those levels of tech and coordination is extremely unusual, or that the ones who do reach that point change direction instead of going on huge expansion sprees. And that leads to a blunt question. If older, more advanced civilizations exist and they still haven't visibly rearranged galaxies or crisscrossed the local universe with obvious infrastructure, What exactly are they running into that we haven't yet? When you combine all the obstacles you've seen so far, insane energy costs, brutal timescales, entropy, social instability, navigation in a moving, expanding universe, it becomes reasonable to think there are hard stops baked into reality. Maybe civilizations hit energy ceilings, where collecting enough power for galaxy-scale projects becomes physically impossible. Maybe they hit stability issues, where large, complex societies cannot stay focused or unified long enough to sustain multi-million-year programs. Maybe they find better uses of their capabilities than brute force expansion, like virtual realities or extreme local optimization. The point is, if intergalactic travel were genuinely practical for mature civilizations, you would expect at least some of them to leave obvious marks, and you do not see those marks. So you end up staring at the Fermi paradox from a different angle. Instead of only asking, where is everybody? You also ask, why is nobody obviously going anywhere on that scale? The idea of a great filter is that somewhere between lifeless planets and galaxy-spanning super civilizations, there are one or more steps that most lines of evolution fail to pass. That filter might be at the start, making intelligent life extremely rare. It might be in the middle, where technological species often self-destruct or stagnate. Or it might be near the top, where truly massive projects like Andromeda-class travel are simply beyond the practical limits of finite beings. Intergalactic expansion is a perfect candidate for a late-stage filter. It stacks every known difficulty: distance, energy, time, biology, sociology, entropy, into one requirement. To succeed, you have to beat all of them simultaneously without any major failure, across cosmic times. If nobody in the observable universe appears to be doing this visibly, the simplest conclusion is not they're all hiding. It is almost nobody ever gets there. Either they choose not to, because they find better paths, or they want to and reality just doesn't let them. So when you dream about sending humans, or anything recognizably human, to Andromeda, you are pushing right up against what looks like a limit seen across the whole sky. The physics math does not explicitly forbid it, but the empirical universe gives you a quiet, consistent hint. If this were actually doable, if this were a thing civilizations could regularly pull off, you would almost certainly see someone somewhere leaving tracks. You don't. And that brings everything full circle back to you, right here, looking up at this neighbouring galaxy and asking whether it's impossible. In strict physics language, it isn't. In every practical sense that matters for a short-lived, fragile, planet-tied species, it is. The last step is to put all those threads together and spell out what that really means for you, for what impossible actually looks like when you stack distance, energy, biology, engineering, and entropy on top of each other. Here's the key twist you've been circling the whole time. Andromeda is not impossible in the strict physics sense, it is impossible for you. The laws of physics do not write a line that says, no object may ever travel 2.5 million light years at less than light speed. In principle, a lump of matter could start in the Milky Way, move through intergalactic space and end up inside Andromeda, given enough time. You can even write down trajectories that work. So on a whiteboard with perfect materials and infinite patience, you can imagine some arbitrarily advanced engineering project that beats every obstacle we talked about. But not forbidden by physics is an incredibly weak standard. Falling into the sun is not forbidden by physics either, but you are never going to do it on purpose. In real life, you have to care about distance, energy, engineering complexity, reliability, biology, and time all at once. When you stack those, what was allowed in principle turns into never happening in practice. Look at how the constraints multiply rather than just add, that's where the dream really dies. The distance forces you toward high cruise speeds, because if you crawl, your trip time goes from too long to meaningless. High speed demands enormous kinetic energy, and the closer you go to light speed, the worse the bill gets. High speed also slams you into dust and gas hard enough to turn tiny grains into explosive impacts, so you need extreme shielding. Extreme shielding adds mass, sometimes orders of magnitude more mass, and that extra mass feeds straight back into your energy problem, because now you have to accelerate and decelerate a heavier ship. Long travel times mean your crew has to survive for thousands, millions, or tens of millions of years, so you need incredibly robust life support, genetics management, psychology, and social systems. That complexity means more hardware, more software, and more ways for things to fail, which again raises your maintenance and energy demands. You never solve one constraint cleanly. Every time you push on one, you make another one worse. You're not dealing with a single hard problem you can brute force. You're trapped in a network of constraints where each fix multiplies the others. It's multiplicative hell, not linear difficulty. Underneath that mess is a simple, brutal mismatch. What you are as a species compared to what the mission demands. Your body is tuned to about 1 g of gravity, the pull you feel standing on Earth. Your lungs are tuned to about 1 bar of pressure, roughly Earth's atmospheric pressure at sea level. Your circadian clock likes about 24-hour days. Your lifespan, if things go well, is under 100 years, maybe a bit more with future medicine. You evolved to solve local problems, getting food, avoiding predators, managing social groups, later building giddies and networks that last maybe a few hundred years at a time before they change. Nothing in your evolutionary history prepared you for thinking naturally in million-year blocks, or living in sealed metal habitats forever, or planning projects over 10 million years. To take Andromeda seriously, you're not just talking about better rockets. You're talking about reinventing what human means. You would need biology that shrugs off radiation and age for thousands of years, or minds that can be uploaded into machines that run stably for ridiculous timescales, or social structures that do not fracture under boredom, drift, and conflict. You'd need people who are comfortable never seeing a real sky, never walking on open ground, never being anywhere except inside a machine. By the time you've engineered all that, you are so far from current humans that the word "you" is almost misleading. It's some successor species built for deep time and harsh environments, not the fragile primate that evolved on this one planet. So what does the universe actually seem to be nudging you toward instead, if it keeps slamming the door on "let's just go there"? The same physics that blocks your Andromeda road trip hands you incredibly powerful indirect tools. Light takes 2.5 million years to cross the gap, but it still gets here. You can build telescopes that collect that light in optical, infrared, ultraviolet, and X-ray bands. You can measure how Andromeda rotates by looking at how its stars and gas move. You can weigh its dark matter halo by studying those motions in kilometers per second and comparing them to how much visible mass you see. You can map its satellite galaxies, trace their orbits, and model how Andromeda and the Milky Way will merge in about 4 to 5 billion years. You can add gravitational wave detectors, which feel tiny ripples in space-time from distant violent events, and neutrino observatories, which pick up ghostly particles that fly straight through normal matter. With those, you get even more layers of information about how galaxies form, collide, and evolve. None of this requires you to send a single human beyond low Earth orbit. It requires sensors, math, and patience. The universe is effectively telling you, you cannot go everywhere, but you can still know a lot if you sit still and listen carefully. That's the last twist. The thing that makes Andromeda both hopeless and strangely powerful as an idea. You will almost certainly never walk on a planet in the Andromeda Galaxy. You will not breathe its air, if any of its worlds even have air. You will not look up at its sky from the inside. For your species, that's off the table. But you can still measure its distance in light years and in kilometers, with enough precision to argue about the 3rd or 4th decimal place. You can read its rotation curve like a fingerprint. You can watch its satellite galaxies swing around it and see tidal streams where it has torn stars away from smaller systems. You can simulate its future collision with the Milky Way in 4 to 5 billion years in enough detail to predict how the merged galaxy might look. So when you try to imagine actually travelling there and everything breaks, that failure is not useless. It shows you just how extreme the scales are, how sharp the universe's limits really are, and how wild it is that from 2.5 million light-years away, sitting on a thin layer of rock and air, you can still reconstruct so much of what is happening out there. Andromeda is impossible for you as a destination, but invaluable as a reference point, a way to see the edge of what a short-lived, fragile, local species can ever hope to touch. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.